Join with computer audio. Start video. Hey, Shane is with us. Shane is with us. I need to adjust this somehow. Maybe like that. That might work. Okay. Does it help to turn on the more lights? Gee, that doesn't help. Neither does that. I guess that's the only thing I can do there. What if I turn that down a little bit? I don't know. What if we poke these up to the sky like that? Oh no, that doesn't help. Let's just leave it alone, maybe. Okay, well, let's see who we got on board here. We have, gee, a good crowd. We've got Alex, Ashley, Ben, Harris, Ben Seaman, Shane, Muhammad, Darren, Brendan, Brian, and Braxton. Got a good crowd. Yeah. Okay. How about it? Do you have any comments or questions, anyone?
Mr. Griffin,
Yes.
how are you?
Oh, fine. Thank you, Mohammed.
Can you go over the torque diagram of 531?
Yeah, I'd love to. Just a minute here. 531.
Yes.
Do you know what page it is?
Just a second. It's on page number 203.
Okay, let me find it here. And it's 531?
Yes.
Yeah. Okay. Well, we know that right now we're looking at problem 531, and we have a lovely equation for power that goes like that. And if you have 3 kilowatts, and you know the angular velocity, it's 50 revolutions per second. But see, we don't want revolutions per second. We want radians per second. So you have to convert that. But when you do that, you'll get the you'll get your torque. Now solving this, I'm going to do this, and I'm getting a torque of 9.55 Newton meters. Ta-da! Okay, and then see what happens is you remove 2 kilowatts, so that only leaves you with 1 kilowatt. And so if you solve this with 1 kilowatt, why don't we label this? That's the torque between B and C. And see, this is going to give you the torque between A and B. And that amounts to 100 pi radians per second. And if you solve that, I think what you get is Mohammed, are you checking me? Am I doing this right?
Yeah.
You getting the same thing I'm getting?
Yes.
Okay, and now what we're going to do is we're going to plot our torque loading diagram. Do we have room here? I probably have room here. And so what you have is you have a torque of 9.55. Well, actually, they have the motor over here, don't they? I should, if I had room, I'd draw the motor. Oh, what the heck, we'll just put it in here like this. You got 9.55, and then it drops down to 3 point something. Your diagram kind of looks like that.
Okay, thank you.
You don't need me anymore. Are you okay now?
Yeah, that's all I need. Yeah, I got it.
Yeah, okay.
Thank you.
Anybody else?
So I had a quick question. This is
Sure, and
Alex.
who am I
So
talking to?
on,
please?
Alex.
Alex, okay, Alex.
Yep. So on the torque loading diagram,
Yeah.
why was the 2 kilowatts on the picture not included? That was my only question on it. Because we included the gear at A in the motor, but
Yeah.
what about the gear at B?
Okay, now let me read this, Alex. I might have done this wrong. I don't know. Just a second here. It says it delivers 3 kilowatts. Gears A and B remove 1 and 2. That 2 kilowatts is what is removed from that gear. You don't have 2 kilowatts. You removed 2 kilowatts. The motor gives you 3 kilowatts, and that gear takes off 2 kilowatts. So that, here, let me draw the motor here. See, here's the motor here. And in this shaft right here, you are delivering 3 kilowatts of power. There's a gear here, and this gear removes 2 kilowatts of power, and that leaves you with only 1 kilowatt of power being delivered in that shaft there. Alex?
Okay. That was my mistake. See, I was getting fixated on the gears. I wasn't looking.
Yeah, that's
really
what is being removed.
Okay, that makes sense.
Yeah, but thank you for asking. Anybody else have a comment or question there? Well, okay. Let's do kind of a review problem, and then we're going to talk about plastic torque. That's the topic for today. But we might want to go over some stuff here that we're supposed to know. Well, what about homework and an exam? You know what? I think there's an exam. It's a take-home exam. It's available Thursday. Today is Tuesday, so it's available Thursday and it's due Sunday. You got plenty of time to do it. No problem. And there's homework too. Homework number 17. Maybe I should write this down. Let me write this stuff down. See, your exam is available Thursday. Today's Tuesday. So Thursday, your exam is available and is due Sunday. And then you have homework. Homework assignment 17. It's problem 567. It's on page 219. And it's due Friday. There we go. Okay. Well, let's do some problems, and the one I wanted to do is 577. Let's do that together. Let me find it here. 577. I'm having trouble finding. I found it. Okay, I found it. This is problem 577. And they have a shaft there. And it's got an external torsion. Actually, there's a couple there. It's 3 kilonewton. Here, I'll draw you a picture of it. It's got 3 kilonewtons. Our artist's rendition here. It's got 3 kilonewtons going up, and then 3 kilonewtons going down. And they are, the distance apart is 100 millimeters, or in other words, 0.100 meters. Now I'm going to ask my wonderful class here. Let me pick on my friend. Oops. Oh, gee, what did I do? Who knows what I did? I want to ask one of my excellents, Samuel, demote. No, that's not right. Demute. No. Unmute. Yeah, that's it. Samuel, unmute and say hi, please.
Good morning.
Hey, good morning. Samuel, there's 2 forces here. They're equal and they're going opposite directions. They're separated by a distance of 100 millimeters. They have a special name for that, Samuel. Do you remember the name for 2 opposite forces separated by a distance, Samuel?
I know that they make a moment, but I am not sure how the forces are called.
It's got a name, a special name. It starts with C.
Couple.
Yeah, that's it. It's a couple. It's a couple. And the way you figure couples, see what a couple is, so Samuel knew this, is it's 2 equal and opposite forces separated by a distance. And they make a moment, just like Samuel said. And the way you figure that moment is you take the force times the distance. Ta-da, and that's all there is to it. You got 3 kilonewtons and you got 0.100 meters. I can almost do that in my head. I get 30. Did I do that right? 30 Newton meters. I don't trust myself. Take 3 e to the 3rd times 0.1 No, it's 300, isn't it? It's 300 Newton meters. See what happens when you do stuff in your head? Okay, we have 300 Newton meters. Now, how do I draw that? I want to draw it with a double arrowhead right here. Do I put my double arrowhead going to the right or going to the left? Let me pick on somebody here. Darren, unmute and say hello, please.
Hello.
Darren, this 300 Newton meter couple, I need to put a double arrowhead. Do I want to go left or right? Darren, you got a 50-50 chance of getting this right.
To the left.
Oh, Darren, you just blew it. You had a 50-50. Darren, stay away from the
Okay, but
roulette
hold on. I
table.
thought the right hand rule, like if you're curving around, shouldn't it go to the left?
And nope, it goes to the right. Darren, stay away from casino. You hear me? You had a 50-50 chance and you blew it. The double arrowhead is going to the right. Now, and it's 300 Newton meters is what it is. Now, how do I know that? Because this is going to try to twist you this way. And if you have a right hand screw and you twist this way, it goes to the right. Right?
Oh, I'm sorry. So the resultant causes the direction, not the forces themselves. Okay, that's my fault.
I'd love to know your thinking, how you got it going to the left.
Well,
how did you do that?
The 2 3 kilonewtons are rotating, the top one's going in and the bottom one's coming out. So I was just thinking, it goes in and then comes out. You do your little right hand rule thing, and I have my thumb pointing to the left when I follow those directions.
Well, I didn't understand that a bit, but never mind. You do understand that it's going to the right. You understand that, right?
Yeah, I forgot I was supposed to be looking at resultants, not like the actual forces on them.
Yeah, I didn't quite understand. You were looking at riddles?
I forgot I was supposed to be looking at the resultants, not the external forces.
Oh, okay. All right. Well, let's get back to our problem now. That was fun. And I got lost here. Let's see. Oh, yeah, here we go. Well, this is A and B, and we got to put in these distances here. This is 0.6 meters, and this is 0.4 meters. And those are fixed connections. So we've got to put in some external torsions. There's going to be one going this way here. How about, I don't know, give it a name, TB, that'd be good. And then there's one going this way here. How about TA for that one? Okay, well, we're all done with our red stuff. And we know what this is. It's 300 Newton meters. And so now let's write some equations. Why don't I get rid of this stuff? You guys can look this up in your Blackboard thing there. Now, don't we need a, wait a minute, before I do equations, don't we need a torque loading diagram? Yes. We need a torque loading diagram. Now, how do you make torque loading diagrams? And the answer is you have to take a left-hand section. So section it in here someplace. There you go. We sectioned it in there. Can you see that's an external torsion. These are external twists called torsions. And you have to have an internal torque going to the right equal to that. So going to the right's plus, so you got TA here, all the way to here. And then what happens is you drop down 300 Newton meters, and then the rest of the way you got, well, see, this is TA, and this is TB. And you can color that in if you like and make it pretty. Here, let me color it. We'll make it pretty. There we go. We have just drawn the torque loading diagram. I don't know much about it. I don't know what this value is. And I don't know what this one is. I do know this here, though. I do know the amount that this thing hops down. It hops down 300 Newton meters. So we have our torque loading diagram. This kind of problem here is called a, it's got a fancy name. It's called statically indeterminate problem. See, we have a statics equation. Let me write it for you. Need some room here. The statics equation is going to go like this. The TA and the TB have got to add up to 300 Newton meters. Now they're going to the left. If you wanted to write that as negative TA and negative TB because they're going to the left, and plus 300 because it's going to the right, equals 0, you could. I was just, I think this is correct though, isn't it? See, if you change the signs on all these, that makes that a minus, and put it on the right side, it's a plus. But that's what it amounts to. Those two have to add up to 300. Y'all, little Southern talk, y'all understand that? That's your statics equation. But you can't solve it because this problem is statically indeterminate. You need another equation. Well, the other equation is called the compatibility equation. I've told you guys all this before. The compatibility equation involves deformations. But in this problem here, it's angular deformations. The angle of twist of section AB, wait a minute, that's not B, that's C. The angle of twist of the part of the rod from A to C, so here's A, C, and there I guess B is over here, minus the angle of twist of BC equals 0. That makes sense? And you could just set them equal. You could just say AC is equal to the angle of twist of BC. You just do a little algebra and there you got it. Now this is called your compatibility equation. That's the fancy name for it. Compatibility equations involve deformations. But we have a lovely equation for angle of twist. See, the fancy name for that is angle of twist. And we have an equation for it. It goes like this. TL over JG. That's it, TL over JG. Okay. Equals TL, it's going to equal TL over JG. All right, and on this one here, I think the JGs are the same. Yeah, the JGs are the same. It happens that the G is 75 gigapascals. They give it to you. If you just tuned in from a daydream, we're doing 577. It's on page 226. And we're cooking up the compatibility equation. So if they're the same, and the J's are the same, they even give you the diameter there, see it? You could just write, we better label these though. See, this is the torque from A to C, and this is the torque from C to B or B to C. There you go, whatever. Ah, these links are different too. This is A to C, this is B to C. Man, if I just had some room, I could do this problem. There's some room right here. I don't need those JGs in there. They're both the same. So what it amounts to is, I call this TA and TB. Let's do it that way. Call that TA, and well, maybe I should keep that L, what is it, AC? Okay, here we go. TA times 0.4 equals TB times 0.6. Okay, now let's box up our equations. Look here, we have two equations and two unknowns. We can do this. We took algebra in school. We can do that. So let's see, TA would be what, 1.5 TB? So you'd have 1.5 plus 1, that makes 2.5. So TB is going to be 300 divided by 2.5. 300 divided by 2.5. I'm getting 120 Newton meters for TB. Now we can get TA. TA is going to be 1.5 times TB, so you multiply by 1.5. I'm getting 180. Now, do these two add up to 300? Well, yeah, that's good. That's good. Now, technically, though, now be careful. One of these is negative. Actually, this one, they're opposite twists. The amounts are the same, but they're opposite twists. And I'm just giving you the amount there. Put a minus there. Can you fit it in? There you go. Okay, now let's finish the problem. What do they want us to do? They want the shear stress in AC and CB. All right. Well, there's a little room up here. Let's do that. They want the shear stress. Well, we have a lovely equation that goes like this. And it's got a name. Let me go to one of my excellent students here. We're going to ask Chase, unmute please, and say hi. Earth calling Chase. Come in, Chase. Uh-oh, coffee break. Darren, unmute and say hi, please.
Hello again.
Yeah, did I just pick on you a minute ago?
I'm ready to get another question wrong if that's what you're asking.
Hey, here's your chance. Here's your chance. Darren, this equation is probably the most important equation in this chapter. What's the name of it?
Torsion or torque, the torque equation or the torsion equation?
Yeah, I think the book calls it the torsion formula.
Hmm.
Good going, Darren. Okay. Well, we can get that for them now. If you want the stress, they want the maximum though. Isn't that what they want? Let me read this. Turn maximum. Yeah. Well, they want it in both places. But if you want the maximum stress in AC, that's going to be the 180 Newton meters. And we need the radius. It has a diameter of 40, so the radius is 20. And this is called the polar moment of inertia. If I might have derived that. I think I did. I think I derived that for you. It's pi over 2.020 to the fourth. That's it. Okay, let's do that for me. I'll give you 30 seconds, and we're going to get the stress in AC. Go for it. Well, I got an answer. I got 14.3 megapascal. And I'm waiting for an uh-huh.
That's what I got.
Hey, there's two of us.
Mm-hmm.
There's a mm-hmm. I heard a mm-hmm. I bet that's right. Now they wanted the stress in the other part. It's going to be smaller. Do we have room here? Yeah, we got some room. The stress in BC is going to be the 120 Newton meters. Okay, plug that in and let's get the stress. And I'll look up the answer book answer and we'll see if we got this problem right. This was 577. Now they said the book got 14.3. Now the book here on this one, they got 9.55 megapascal. Anybody get 9.55? Say uh-huh.
I did.
That's the book and you agree. I didn't do it. Anybody else get 9.55?
That's what I got.
Yay, good going. Well, we whipped that problem. Well, let's do another one. Well, I need to talk to you about plastic torque, though. Let's do that. Was there anything else anybody wanted before we talk about plastic torque? Okay, I need the room. Let me get rid of all this stuff if you're happy. So you're okay with all that? All right, let me get rid of some of this stuff. Now the topic is plastic torque. They might call it something different. Let's see what they call it. I'm flipping through here. The book calls it inelastic. That's what the book calls it. But I think they use the term plastic too, if you keep reading in there someplace. Now to explain it, you all know when you're dealing with materials like steel, these metals, they have a yield point. They come up here, there's an elastic region, it's a nice straight line. We're talking about shear stress versus shear strain. And then they go flat for a while. They do that right there at the yield strength. The name of this is the yield strength shear stress. That's the name of it. It's the yield strength shear stress. Now this right here is called shear strain. This is shear strain. There's a place right here called gamma with a little y under it. That's called the yield strength shear strain. Now when you take a round rod, I'll draw you a picture here. Take a round rod, there you go. And you put it under a lot of external torsion. Well, if you increase that torsion, what happens is the torque increases inside your piece. That means the stress increases and the strain increases. If you put enough twist on a rod, you can reach yield strength. And you'll reach it first on the outside because stress is equal to T rho over J. And does it make sense that if the rho is the maximum, then you'll get your maximum shear stress? So what happens is you start picking up a thin outer ring here, you might call it, of it yields. See, it yields in this outer ring. Now, if you keep increasing the torque on this rod, this thing grows, and you get a bigger region of. They call it the plastic region. In fact, they have a name for it. It's called the. This is called the plastic. Okay, now I'm having senior moments now. Just a minute. Let me think of the name of this stuff. Yeah, it's called the plastic annulus. And if you increase the torque even more, the plastic annulus grows even more. And you understand it's plastic. It's still elastic here. It's still elastic there in the center. And they have a name for that. They call that the elastic core. It's called the elastic core. And this other part is called the plastic annulus. I know you've seen trees that have been cut down and they have these rings. They're called annular rings. And you can tell how old a tree is by counting the annular rings. Well, they call this the plastic annulus. Okay, great. And then they developed the equation for it on page, it's actually on page 246. I'll outline the development of their equation, but I don't know if I want to go through the minute details. This is going to give us the equation for what we're talking about here is elastic plastic torque. Let me give you three things that can happen. You can have elastic torque, in fact, if you increase the external torsion on a rod, you'll reach a place where you'll have the maximum elastic torque, and the symbol for it is T with a little Y on it. Now, if you increase the torque in a piece more than the maximum elastic torque, you'll get what they call elastic plastic torque. And the symbol for that, this is all on page 246. You guys could read the book. There you go. That's the elastic. That's what this is. See, it's part elastic in the center, and it's kind of part plastic around on the ring there, and the plastic annulus. And then finally, if you keep increasing the torque on a piece, you'll reach a place where you have the fully plastic torque. The fully plastic torque. And the symbol for that is T with a little P underneath it. You see, here's the deal. If you keep increasing this torque on this piece, the elastic region shrinks. Ooh, look, the elastic core is getting tiny. And there's a place, if you keep increasing the torque, it's just a dot and it disappears. It's a little bit like the Cheshire Cat on Alice in Wonderland. It just vanishes and disappears. You reach a place where the entire rod goes plastic. Now, if you reach that place, you got a problem, because that rod just twists like butter. Okay, it's like taking a stick of butter and twisting both ends, and you got a problem. I think there's a picture of there's a picture in here, I thought, of a drive shaft that had reached that place where it went entirely plastic, I saw it in your book, but I can't find it. And it just basically twisted to be it was worthless. I can't find it. I can never find anything. But you can kind of visualize it. If the torque got too much, it would go plastic and twist, it basically twist off. And you got yourself a big problem. Okay, I can't find it. Never mind. Give up. Okay. All right, well, let's see if I can outline that development there. Now you're going to have to break it down into two parts. The elastic part and the plastic part. Now, in the elastic part, the way it works is the torque in the elastic part you would have to sum up all of the distances I don't know if that makes any sense. But see, when you take stress times area, what you get is a force. In this case, it's a shear force. You could write dV if it made you happy. And so if you take a distance times a force, you get a torque. And in this case here, the shear stress would equal this. They have a name for this radius right here, by the way. This is called the radius of the elastic core. Rho sub y. That's the radius of the elastic core. And see, the stress is going to equal the, and you see, you'll reach yield strength stress throughout in here. It's plastic. It's going to be tau sub y times rho over rho sub y. I think that's it. Yeah. Because see, when the rho is 0, you got 0 stress. And when the rho is equal to the rho sub y, then you just get the yield strength stress. So if you plug that in there, ran out of room there, made my diagram there. I've got an integral of rho tau sub y, rho over rho sub y. I probably shouldn't be doing this because it's pretty boring. Now the area, you know how they do in calculus. They make these little rings and they add them up. And see, that's an area dA. And you know what it's equal to? It's 2 pi rho d rho. It's the circumference times the thickness. So if you plug that in there, what you got is rho tau sub y, rho over rho sub y, 2 pi rho d rho. And you're going to go from 0 to rho sub y. That'll give you the torque in the elastic region. Now the torque in the plastic region is a lot easier to figure. Let me make some room here. I'm just outlining. You guys can read this for yourself. You don't need me. The torque in the plastic region is a lot easier. What it is the integral of, you're making these little thin rings in the plastic region now. It's your distance rho times your force, which is which is equal to toss of y times 2 pi rho d rho. See, that's the area. That's your dA. And tau times dA gives you a force. Rho times the force gives you the moment. Now, if you'll take this and you'll add it to this, you will get what they have on page 246. And instead of going through all that boring algebra there, can we just cut to the chase and give you the result? Here it goes. This is the elastic plastic torque. It is equal to this is a nice equation. Write it down someplace where you can find it. And then we'll work some problems with it. How they got this is they took this and this, they added them, they combined terms, and they got this. It's there on the bottom of page 246. That's how they got it. All right, now that we have that, let me talk about it for a minute, and then we'll work some problems. I'm gonna erase all this jazz. And what's neat about this equation, it's on page 246, like I've said. You can get the fully elastic torque and the fully plastic torque from this equation. This is called the maximum elastic torque. And what that is where you don't have any rho sub y. You don't have any radius of no. I got that backwards. The radius of the elastic core is equal to c. Here, let me write it. The radius of the elastic core is the whole radius c. Do you remember they decided to call this radius c, and any other radius they called it rho? Well, if the whole thing is elastic, and that's a c, you got 4c cubed minus c cubed. That's 3c cubed. So you get pi over 6 tau sub y times 3c cubed. Do a little algebra and you get pi over 2 tau sub y c cubed. Now that should be the equation for the maximum elastic torque. Let's see if it is. Look on page 246. Page 246. Do you see that equation? Pi over 2 tau sub y c cubed. It's right there on the top of the page. It's called the equation for the maximum elastic torque. Ta-da, and there you have it. You can get it from this equation for the elastic plastic torque by letting the radius of the elastic core be the entire radius. The whole thing's elastic. Now you can also get the fully plastic torque by making this radius 0. There is no elastic core. If you make that 0, here's what you'll have. You'll have pi tau sub y over 6 times 4c cubed. See, this goes bye-bye. You don't have any elastic core. Or you could write this as 2/3 pi tau sub y c cubed. Can you find that equation on page 247? 2/3 pi tau sub y c cubed. It's on page 247. And then somebody noticed, if you compare these, it turns out that the fully elastic torque, no, the maximum elastic torque and the fully plastic torque are equal to 4/3. See that equation on 247? No, I got it wrong. No, it's 3/4. I got it backwards. Well, that's interesting. Enough theory. Let's work a problem now. Here we go. This is problem 5.135. We're going to do problem 5.135. We're going to use all this wonderful theory. But before we do we have any questions or comments? Well, I didn't hear any. I guess either we're taking coffee breaks or who knows what. I'm going to erase all this because it's all in your book, and we don't need it. Okay, now here's 5.135. You've got a rod that's 3 foot long. Let me draw it here for you. It's 3 foot long. There you go. And they've got some torque, some external torsion, and it's doing this. It's an external torsion. Put double arrowheads on there. Do they tell you what it is? 3-inch diameter. It's a 3-inch diameter shaft. Let me write that. It's a 3-inch diameter shaft. We're going to do problem 5.135. It's on page 255. They want the radius of the elastic cord. This is causing a torque of 18 kip feet. So this external torsion is 18 kip feet. All right. Now, they gave you the shear stress, shear strain diagram, and it went like this. This is 0.006, and this is 33 KSI. Okay, now we're going to find the slope right in here in the elastic region. We might need it for something, I don't know. We're going to pause, and I want you to find G. They have a name for it. It's called the modulus of something. Rigidity, the modulus of rigidity. Okay, I'm going to shut up. Find the slope of that graph there in the elastic region. Go ahead. And I'm going to pick on one of my wonderful students here. And let's see. Ben Seaman. Ben Seaman. Unmute and say hello, please.
Good morning.
Good morning. Hey, Ben, have you found a slope of that elastic region yet?
I got 5.5 MSI.
You know what? He's got it right. It's 5.5 MSI. Now, do I need to explain that to anybody, or are you all happy with that? Okay. I guess you're happy. Now, let's write our equation for elastic plastic torque, shall we? Now, the way you do that, I forgot the equation. It's pi toss of y over 6, maybe. I'm doing this from memory. It's pretty scary. C cubed minus, oh, brother. I better look it up. Let me look this thing. I showed you how they came about this equation. And it's, hey, I started off good. Oh, there's a 4 right here. See there? There's a 4 right there. I was going to miss that. Minus rho sub y cubed. That's your equation. That equation's on page 246. It's the equation for elastic plastic torque. See, they've got, inside this thing, they've got an elastic region inside here, and then they have a plastic annulus. It's part elastic and part plastic. And we know what all these symbols mean. This tau sub y, what that is the yield strength shear stress. This C here, we know what that is. That C is it's the maximum radius of your rod. And this rho sub y here, that's the radius of your elastic core. Okay, well, let's plug it in. Here we go. We know what this is. It's 18 kip feet. 18 kip feet equals pi. And now we know what this is. It's 33 KSI. That's what this is. This is tau sub y. Yield strength shear stress. 33 KSI over 6. 4 times. Now, if the diameter is 3, that means the radius is 1.5. You have to cube it, minus rho sub y cubed. Okay, now we have a lovely equation here. See it? There's only one unknown. The unknown is this radius of the elastic core. Yeah. Okay, I'm going to shut up for a minute and a half. Get your calculators out and solve for this radius of the elastic core. I'll be quiet. Go ahead. Well, I don't know if I gave you enough time, but we never have enough time to do stuff. Now, I pulled a kind of a dirty trick on you guys. The units don't work. See, this is kip feet, and this is going to be kip inches. You can't set kip feet equal to kip inches. But what you can do is if you multiply this side by a foot and you divide it by 12 inches, then you have kip feet on both sides. Now, if you're smart enough to have figured that out, you're a better man than I am. But you've got to pay attention to units. Now that I've shown you that you got to put that 12 there, I'll shut up again and I'm gonna let you try it again, because I bet some of you didn't do that 12 there. If I know human nature, you probably didn't. So I'm gonna shut up again with that 12 there. Find the answer for me. What we're solving for is this unknown, this radius of the elastic core. It really helps to have that 12 there. Well, with that 12 there, let me go to somebody here and see. Ben Harris, unmute and say hello, please, Ben.
How's it going?
Doing great. Hey, Ben, were you able to, did I give you enough time to plug that in and find that radius of the elastic core?
Well, I'm not sure if I was able to just multiply by 12 at the end, but I got 27.82 when I did that.
That's not what I got. Do
I'm
it
reworking it
again.
right now.
Do it again. So you take 18 times 6 times 12, and then divide by pi, divide by 33. And then you're still not done. Well, let me pick on somebody else here while Ben's working on that. Braxton, unmute and say hello, please.
Hello.
Hello. Hey, Braxton, were you able to come up with an answer for your radius of your elastic core?
Yep, I got 1.00 inches.
That's it. Let me draw a picture of it. See, here's your rod, and you know that the radius is 1.5, diameter is 3, and the radius is 1.5, and you go out here 1 inch, and you're looking at the elastic core. Here it is, the elastic core. And if you go back here and look at the answers of 5,135, we'll see what the book says. They said 5,135. They said 1 inch. Actually, when I did this, I got 0.99, a whole bunch of nines. I just rounded it off to 1 inch. Anybody else coming up with 1 inch? I want to hear some uh-huhs.
Mm-hmm.
There's one. Anybody else able to get 1 inch out of that?
That's what I got.
Yeah, good. I need one more uh-huh. I could write it out more carefully if you wanted me to.
I got
That's
it.
what I got.
Okay, I heard two of them. I bet we're okay. I bet you can do that. Now they wanted something else. They wanted the angle of twist. Let's do that, shall we? How are we fixed for time? We've got 11 minutes. We might make it. We might. You can do a lot in 11 minutes. I need some room though. Got to sacrifice something here. Now we have a lovely equation for angle of twist. It goes like this. Do you notice in this equation, they have the modulus of rigidity in there? That equation is only good in the elastic region. But see, this thing, it does have an elastic region, but it also has this plastic region. So you can't use that equation to find the angle of twist. You'll get the wrong answer. This equation only works if you have, if you're in the elastic region strictly. However, I taught you another equation long ago when we were younger and better looking. If I can only remember how it went something like this. Shear strain is equal to, well, it's equal to deformation over length. And in this case, that deformation is perpendicular to your length. It's equal to rho, we'll use a theta. I think the book used a phi. And I'm sorry to erase that, but they in their stress strain diagram, they give you this. It's got a name. It's called the yield strength shear strain. They give you that. Now, if you put that in there, you're going to have to put in rho sub y, which is your radius of your elastic core. So here we have this equation, and we can solve. This equation does not depend on being elastic or not. It works whether you're elastic or not. Okay, let me write it and we'll solve it. Here goes. You can't use that one. I got a little room right in here. This here is 0.006 on the graph. I had to erase it, but you've got it there in your books. It's on page 255. 0.00. I got lost. Yeah, here I'm doing this equation here now. Never mind this one. Don't get mixed up. I'm doing this equation here. It's 0.006. Nothings, because remember, strain is dimensionless. And we know this radius of the elastic core, it's 1 inch. And we know the length, it's 3 feet. We can't use feet. We've got to turn that into inches. Well, 3 feet is 36 inches, right? Yeah. So write that 3 feet down as 36 inches and solve this equation for theta and tell me what you get. That'll be the angle of twist. Go for it. Well, I got an answer. I got 0.216. But what are the units on that? Let me have
Radians?
some. Go ahead.
Radians.
Yeah, they're radians. Right. That's radians. Now, if you wanted degrees, you're going to have to, if that's radians, you're going to have to multiply by 180 degrees is pi radians. Okay, well, now I'm going to get the degrees. Here we go. Times 180 divided by pi. I'm getting 12.3 degrees. This rod twists 12.3 degrees. Now look up the answer in the back. This is problem 5, 135. And they said, five 135. They said 12.4 degrees. Gee, I wonder why we're off by 1/10 of a degree. Let's don't fight over it, I guess. The book says 12.4. They must have rounded something off. I don't know what they did. I think we did it all right. Now, if I had time, I would show you there is a way to use that angle of twist equation. Here, let me outline this for you. We have a lovely equation that goes like this, but it only works in the elastic region. Well, see, we do have an elastic region. The elastic core is an elastic region. We could use this equation if we restricted our work to the elastic core. How much time do I have? 4.5 minutes. That might be enough time. Now we've got G, and if you restrict yourself to the elastic core, I think we could get it. Let me show you what the J would be for the elastic core. It would be, now how do you do that? Pi over 2. And in this case, it would be 1 inch, right? To the 4th. Isn't that right? Yeah, I think that's right. Pi over 2, 1 inch to the 4th. So we know the J. We know the length. The length is 3 feet. Now you probably need inches, 36 inches. But see, we know that. If we could only get the torque provided by the elastic region. But here's the tricky part. This torque of 18 kip feet, I need the room here. We're going to have to sacrifice something. That total of 18 kip feet is provided by the torque in the plastic region plus the torque in the elastic region. And it's the torque in the elastic region is not equal to 18. We would have to know how to divide these up. Well, I could show you how to do that. I need some room though. It's not that hard. Actually, it's easier to get the torque in the plastic region and subtract, and then you could get the torque in the elastic region. If we could get that, we could find the angle of twist. How am I doing? I got 2.5 minutes. Well, here's how you get the torque in the plastic region. It would be the integral from 1 inch to 1.5 inch of rho times tau sub y, which we know. Tau sub y is 33 KSI. It's on that graph thing there. Times your area, which is 2 pi rho d rho. See, if you take your stress times your area, that's your area, dA, circumference times thickness. That'll give you your force times your distance gives you your torque. This you could solve. We know what that is. That's equal to 33 KSI. And we know we could integrate this if I had time, but I don't. We could solve it. We can get the torque in the plastic region. Once you know that, you could get your torque in the elastic region by subtracting. Once you have that, you plug it in here. You could get your angle of twist, but wasn't it a lot easier using this? Much easier. It's sad, but our time together has come to an end. I'm going to have to say goodbye to everyone. I hope you had fun. I did. Okay. Any last words? This is it. 5, 4, 3, 2, 1. Goodbye, students.
Bye. Have a good
Goodbye.
Thank you.
very much.
Goodbye.
Bye for now. See you on Wednesday at 9:30. Okay, it's a deal.